fejleszteni, de ez az Anglo Society nem akart el az egész szerződés, ez nem látszik, hogy felelősség, nem akarsz akkor az eredményet, és emiatt igazából a mondhatás ez az
Welcome everyone. We are pleased to have Leanne at the Institute of Science. So with that, stage is yours.
Thank you. So thank you everyone for coming. The paper I'll be presenting is joint work with Robert Schmidt from Fernuniversität Hagen. So the idea of this paper is, I don't think I really need to tell you that climate is like a big topic these days. And I mean, if we look at the EU or like these kind of climate summits, there's been for many years attempts to reach some kind of climate agreement to all cooperate and try to reduce pollution together. And so this paper is part of like a strand of literature that looks at this attempt to form these kind of climate coalitions from a theoretical perspective and try to like analyze what you would expect to see and what might be like the problems there. So climate cooperation is a typical public goods problem in the sense that if you have to reduce your emission, that costs you, but everyone is benefiting from you reducing your emissions. So your ideal scenario is that you don't do anything and everyone around you puts in like full effort, you fully benefit from what they do and you don't have to cost yourself. So that's of course why it's somewhat difficult to actually form these kind of climate cooperations between different countries because there's the wrong types of incentives, typically speaking. Now, people have been like writing theoretical papers about this for quite some years. And if we look at some of the earlier models in this strand of literature, the predictions were actually like very pessimistic. So there's this paper by Barrett from '94, which was not just necessarily about like climate coalition formation, but what his model shows, or like in his setting, is that you would typically only get very small coalitions, like maybe 3 or 4 countries. And the sad thing about the prediction of that model is that exactly when the potential benefits are very large, that's when you would expect a relatively small coalition, because then the incentives for free riding are also large. And this is what has been dubbed the paradox of international agreements. Exactly when you have the potential of reaching large benefits is when you don't actually manage to. If we look at what's happening in real life, that's not necessarily what we see. I mean, of course, like there's been some climate summits that people considered a complete failure, but there has been some actual agreements with actual like large groups of countries signing that agreement, vouching that they would cooperate to try to reduce their emissions together. So there's something about this like early model that's clearly not capturing the full reality of what's happening in these climate negotiations. So I will refer to this model by Barrett as the static game. We use it as a kind of like a benchmark in our paper. So that's why I want to like quickly explain to you what this model actually says. I don't know if I have a pointer here. I have a pointer. Okay, so the static model is a simple one-shot game. Everyone simultaneously decides if they want to be part of the coalition or not. And then after they've made that decision, the ones that decided to join the coalition will now cooperatively decide how much to reduce their emission to like maximize their joint benefit, whereas the ones that decided to stay outside of the coalition are just strategically maximizing their own benefits. So that's the simple situation here. And so that's exactly the model that I just mentioned, where like if you look at just that, the predictions are that you get like 3 or 4 countries in equilibrium in the coalition and the rest stays outsider. So in the last couple of years, there's been some papers that reach more optimistic predictions that fit reality a bit better. I'm mentioning here 3 of them. There's the paper by Battaglini and Harstad. So what they have in their model is that there is more time, so to say. It's not just a one-shot game. So actually you have like several periods, and when a coalition decides to sign an agreement, they don't just decide to sign an agreement, they also decide for how long they're gonna sign that agreement. And on top of that, part of their model is also investment, which is not usually part of the agreement. And so what they get is that there's like a hold-up problem where you want to reach an agreement for a longer period so that you incentivize countries to actually invest, because if the agreement is short, then you don't want to invest yet because you'll be in a worse position next time there's negotiations. So this combination of factors leads their model to have more optimistic predictions, where you get larger coalitions that sign longer term agreements. Then there's this paper by Kovac and Smith. It's in many ways simpler. They only talk about emissions. And the main thing that they do is that you just have several periods, meaning that you have the choice to not sign an agreement today if you're not happy with the size of the coalition. That just means that there's no agreement now, and you're going to negotiate again after a certain delay, let's say next year. So of course, there's a cost for the delay. But then you can try again in the future, and simply having this option as a coalition to say, no, we don't want to have a coalition with just 3 agents, so we're not going to sign it right now. So we're all going to like have the downside of not having an agreement right now. That's a way for the coalition to put pressure on potential outsiders to join the coalition and make it larger. So just by having these several periods, they already find that you can have more optimistic results, and you get larger coalitions in equilibrium than in just the static model where you just have this one chance to make an agreement. So both of these, by the way, as some of you might recognize, still have that in equilibrium, an agreement is signed right now. So they solve the paradox of that you only have small coalitions, but they don't have any option for a delay in formation of an agreement, which we do see in reality. This is one thing that I think is nice about the paper by Karp and Sakamoto, is that their model actually allows for a delay in the formation of an agreement in equilibrium. And what they do is they have every period with some probability a certain size forms. And so every period you can decide as a coalition, like, do I want to keep the agreement that I have, or do I want to like abandon it and try again? And so what you get is that if like a small coalition forms, they will sign for now, but they will abandon it again in the next period in favor of the option of forming a larger coalition. And so they get this possible delay because it might take a bit before, by chance, you actually get a large coalition, which you don't want to abandon anymore because the chance of getting something worse is high enough. Okay, so that's 3 papers that really have more optimistic results. What we found was kind of missing in this is that they all work with these individual periods, and in the period itself, it's still a one-shot game. So of course you have time being a component of the model now, but it doesn't allow you to look at what happens during the formation. So there's still this sort of like black box thing where, oh, a certain set of agents suddenly joined, and now we do something with that result. So we wanted to look into that black box and see, like, if we try to model that actual process of forming a coalition, what will we get out of that? This is what I just said. Okay, so what we do in a like sort of quick summary, we take every period as one period is now like a continuous time frame. And so during that continuous time frame, countries can join over time. So where before a country only had the option, do I join or do I not join? Now a country also can say, when do I want to join? So there's like two parts to the decision that you can make. We still look at a model where only one single coalition can form. And now, because we have this continuous time, we have 2 ways in which the game can end. Either at some point there is a coalition that decides to sign the agreement, or with some exogenous hazard rate, the negotiations fail. The idea behind this exogenous hazard rate is that if you look at these these climate negotiations, what you oftentimes see is that on the last day of the summit, they negotiate until 4:30 in the morning, some random end time that no one pre-specified, and then all of a sudden the decision is made that, oh, we're not going to reach an agreement, this is a failure. So that seems like, just to sort of not have like a clear-cut endpoint, we model that as a hazard rate. And so what's important to realize is that in the static versions of the game or the one-shot game, a coalition forms and then you decide to sign or not. Whereas with us, it's like a sort of continuous choice of the coalition. Do I want to, as a group right now, sign an agreement, or do I decide to wait a bit longer with this group that has vouched that they do want to sign an agreement at some point? What we find is that the model allows for the formation of very large coalitions. This is under like a pure strategy equilibrium that we define. And there we can even get like the grand coalition to be an equilibrium size, which might be considered a bit overly optimistic, but I think from a theoretical perspective, it's an interesting result. And then we also look at a mixed strategy equilibrium, where we try to define what are the equilibrium conditions. So that's a bit less sharp. We don't have very like sharp results and like this is the size that you can reach. But what we see is if we look at some specific cases, is there actually you kind of go back to the more pessimistic results if you only find small coalitions in equilibrium. But what we do get there is a possible failure on the equilibrium path, which is new compared to like previous models in the literature, which never sort of had the option of actually having a failure on the equilibrium path. And then again, we look at an extension where, because these first two are still a single negotiation round, but just the negotiation round itself has continuous time. So we look at an extension where we add these multiple negotiation rounds that I just mentioned, like other papers already had. And that has a positive effect on your possibility of reaching like larger coalitions in equilibrium. It's still ongoing work, so there are some results that we still want to see if we can get, but we're not sure yet. So I'll just share with you what we have this far. And let's get into like the more precise details of the model then. So we have n countries, which ex ante are symmetric to keep the model simple enough. And we have continuous time that has no specific end time. Then there's discount rate, R, and a probability of failure, which is the hazard rate sigma, which is exogenously fixed. Then throughout the presentation, I will use K to denote the current size of the coalition. Of course, technically K depends on T, but it will never be confusing, so I'm not actually writing that in T. Yeah?
So, just a bit of your idea, the time frame is like summit or something like that, right? It's not several years. In
Yeah.
this case, it's just a couple of days or a couple of weeks.
Yeah. Yeah, I wanted to think of the time as like a summit that lasts for like several days with an unclear end time of the summit.
Relevant, the discount, I mean, you probably need the model, right, just to get a result, but you can't.
So for a large part of the model, having a discount rate and a probability of failure is a bit double. You could do with just one of them. I think when we look at the repeat negotiations, it starts to matter that we have both. And that's
Yeah, but then it's also not enough.
yeah, and then like your probability of failure is not an actual failure anymore. It's we go to the next round. So that's why there it starts to matter. That's why I keep both of them in the model. But like for the single negotiation round, it's technically superfluous to have both of them. Yeah. But I think it helps if I start with them so that like it's already in the model by the time we get to the repeated rounds. Okay, so then we have a reduced form kind of model. So I'll use pi0 for payoffs, or like pi for different types of payoffs. Pi0 is the payoff that you get, the flow payoff, while no agreement has been reached yet. And it's the same that you get if the negotiations fail, then you get that flow payoff for like eternity. And then if an agreement is reached, then from that point on, the coalition members get pi s of k, where k again is the size of the coalition that signed the agreement, and the outsiders get pi n of k. So this is what I said, like it's a reduced form, it's like not really explicitly saying what's the underlying emission gain. Oftentimes I refer to like the large pi, which is just the discounted version of like the net present value of these terms. So just to set the idea a little bit, because most of the time it will just be this like big reduced form, like this is an example of what you could think of as an emission gain. You might have like a benefit function where your benefit from emitting a certain amount, EI, is this function. And then you have a cost of like the total pollution, like large E is the sum of the small EIs, which can look like this, for example. This is one example. I mean, there's different versions in literature. And I will make some assumptions on the pi functions just to make everything well behaved and fit with the kind of situation that we're looking at. Okay, so the assumptions that I'm making on pi, first of all, I'm assuming that there is some lower bound, and above that lower bound, it's always better to be an outsider than an insider for any level of the coalition. So that's just modeling the free riders incentive. Why do we have this K0 larger than 0? Because if you fill in specific emission gains, you will find quite natural functions that have a K0 that's actually good. So to allow for that in our model, we allow that K0 might be somewhat, it's obviously usually small, but it might be a little bit larger than 0. Okay. Second, we assume a form of monotonicity, which is that a larger coalition size is better for the outsiders, for the insiders, and for the total amount of welfare of all of society. Then thirdly, this is like a single crossing property. So we're assuming that there is a K tilde. At K tilde, you're indifferent between remaining an outsider or joining the coalition and becoming an insider. And if we are below K tilde, then you would rather join that coalition than remain the outsider. And if we're above that K tilde, then you would rather stay out. And moreover, this difference becomes larger, the larger K gets. And then lastly, we need some sort of bound on the pi 0. A very natural one is that pi 0 is smaller than pi s of KST. What is KST? KST is the equilibrium size in this static one-shot game that I mentioned in the beginning. And KST is like the first integer that's larger than K tilde. So that's the main ingredients of our model. Then to get back to the static model from the beginning, there finding the equilibrium size is relatively straightforward in the sense that the size that's an equilibrium size satisfies two conditions. The internal stability condition says that if you are part of the coalition, you would not benefit from leaving the coalition under the assumption that the remaining agents would still sign. And the external stability says the other way around, that the ones that are outsiders would not benefit from becoming an insider under the assumption that the coalition would sign in that case. And so this condition is exactly satisfied by KST. If K tilde is an integer, then there's technically two solutions. We're going to assume for this paper that there's only one solution because it just makes the whole story a little bit easier. But it doesn't, in the end, it doesn't matter that much. Okay. So then, and we need to talk about the strategies, of course. So in our model, your action space is fairly simple. If you are not part of the coalition, at any point in time, you can decide to join, or you can decide to not join at that point in time. So I'll call that stay out or wait. If you're part of the coalition, you can decide to vote for signing the agreement, or you can decide to vote against at any point in time. We assume that an agreement is signed only if all the coalition members agree. And we also assume that once you join the coalition, you won't leave again, just for like the kind of strategies that we consider. Of course, when we talk about whether it's an equilibrium, we do look at whether you would have benefited from not being part of the coalition. But this is, in our model, and the type of strategies that we're going to look at, you don't benefit from joining and then leaving again. In that case, you could have just as well stayed out to begin with. And so it's kind of without loss of generality, but it just makes the analysis a little bit easier. So as a side note, by the way, we're not in this paper characterizing like all possible equilibria strategy. We're just going to be looking at specific strategy profiles and arguing whether or not those are equilibrium strategy profiles for certain sizes of coalitions. Okay, and then the last thing about the strategies is what we focus on is strategies that do not specifically depend on calendar time, and they do not specifically depend on when other countries have joined the coalition or in which order. They may depend though on which countries have joined the coalition, but you just don't care about when they did that or what order they did that in. That's just a restriction again on like what kind of strategies we look at, like not really when we look at if it's an equilibrium, of course, everything is allowed. Okay, then one last assumption, which I think is a fairly natural one, to just rule out coordination failure. We assume that if a country is part of the coalition, and if it would be better for this country, weekly better to sign with this coalition size rather than to wait a bit longer, then we're going to assume that he always votes for signing just to not get like weird equilibria where you get each other locked out of an agreement. What you could also think of is instead of everyone needs to agree, if we have one representative that's going to vote for us, whether we want to sign or not at this point in time, that's essentially the same kind of setting. Okay, and with that, we're ready for, oh no, sorry, one general result before we're ready for like the actual strategy profiles. So one general result that we get for this model is that in our model, we cannot have an equilibrium where a coalition signs an agreement that's smaller than what you would get in a static game. So no K star smaller than this KST, the equilibrium size in the static game, could be an equilibrium size for signing an agreement in our setting. And that's simply the case because external stability is still playing a role in that case. External stability is violated when we are below KST, meaning that an outsider would benefit from joining the coalition, assuming that they would sign. And if you assume there's no coordination failure that I just mentioned, then this external stability is always an actual factor that plays a role.
Sorry, so when you say no strategy profile, meaning Markovian strategy, or any strategy profile?
Any strategy profile, as long as you assume this no coordination failure assumption that we just. So it's
also
not
the ones that are not Markovian.
Yeah. Okay. So then I first want to tell you about the pure strategy equilibrium that we find. So it's a relatively simple strategy. We assume that there's some K star that everyone knows about. This is the K star that we're supposed to reach. And there's some K star amount of countries that have been assigned to become a coalition member. This is common knowledge. And the strategies are now that those K star assigned countries are going to join immediately at any time T. And once they've joined the coalition, they're going to wait for all the other K star countries to join. Once they all join, they're going to vote for signing the agreement. The ones that were not assigned, they will never join. If in some off-pot scenario, they would accidentally join, they do the same as the assigned countries. They vote for signing if and only if all assigned countries have joined. So under this strategy profile, you can get a kind of self-fulfilling expectation equilibrium where any K star that's at least as large as this static game K is an equilibrium under this strategy profile. Simply because if everyone expects you to join, you don't have any benefit in waiting and staying out because they're not going to sign unless you join. And so you don't benefit from doing that. And because we have continuous time, you can always wait a second because you expect this person to join any minute now. So it's kind of costless to wait, and it's not beneficial to stay out because then you would just get 5-0, which is way worse than being part of the coalition. So this is in a sense a nice result. What I mentioned before, it seems a little overly optimistic to assume like all countries to join. But to some extent, it does also seem natural to me that in real life, there are some countries where you would always expect them to join. And so there's no point in them trying to pretend that they're not going to be part of this agreement because everyone knows you're supposed to join anyway, and it, I don't know, it fits your style and stuff like that. So I think there's some point in this kind of strategy. But it's probably not the whole story. Yeah.
How are your results sensitive to the fact that you have symmetric countries?
So I would say in this case, it doesn't matter for the pure strategy case. The pure strategy, this equilibrium just hinges on the fact that you have continuous time. And I'm quite sure you could do the exact same with like non-symmetric countries. For the mixed strategy scenario, I think asymmetry might play more of a role. I haven't exactly looked at that, so I'm not 100% sure. So then we have a mixed strategy profile that we look at. So here there might still be some alpha assigned countries which are expected to join immediately. They have the same strategy as the assigned countries before they join immediately, and with the one difference that now they're part of the coalition, they don't just wait for the assigned countries to join, but then they wait a bit longer because they want to reach some larger number of data. And then now for all the non-assigned countries, we're gonna assume that they first wait for all the assigned countries to join, which in principle should happen at time 0, so there's no real waiting there. But then after that, they play with a mixed strategy with a positive hazard rate, which I will call H. And so over time, these countries might join one by one. And then once the coalition has reached size theta and all these alpha countries have joined, it will sign an agreement. That's the idea. Yeah.
So that means your integration of mixed strategies, and this is, they're mixing independently every single point.
Yes. So their mixed strategy in this case is a hazard rate,
Yeah.
which is the best equivalent of a mixed strategy that I have for continuous time. But yeah, I mean, they also, because they're symmetric, they will all be playing the same hazard rate, but it's independent. So like, because it's continuous time, they will only join one at a time. The probability that they join at the same time is 0. Okay, so now we'll analyze what kind of equilibrium we can get out of this, or what conditions we need for that. So we need 4 conditions for this to be an equilibrium for a certain theta. First of all, we need external stability at theta. That's relatively easy to satisfy because that's true for any theta that's at least the size of KST. Then we need that the theta coalition members would not have been better off if they had not joined or by leaving again. That's just satisfied because the strategy says that no coalition is going to sign an agreement if they're smaller than theta. So if you would not be part of the coalition, then you would just all get by 0. And then we need 2 more things. We need that the non-assigned countries are indeed willing to mix, so they need to be indifferent. And lastly, we need that the coalition members are willing to wait until they've reached the size of theta, that they're not like interested in signing earlier because that gives them a higher expected payout. So I will first look at the first one, the mixing. So for that, we need to look at the continuation payoff. This looks like a lot, but I'll run you through it. So effectively, if you are part of the coalition, then you get the expectation, the continuation payoff W as theta K. And I advise you to look at this one because I think it's a little more readable. So effectively, you get a flow payoff of R times pi 0 while the game is running. Then if there is a failure, the sigma, you get pi 0 for forever. And then with some probability, someone is going to join, and then you have continuation payoff of 1k larger. What's that probability? There's n minus k countries that are still outside, and they each randomize with the hazard rate h, which is a function of theta and k. And so this is effectively like a weighted average of these factors. So for the outsiders, we get something that's quite similar. The main difference is that there is some probability h theta k that you are the one that joins, which means you get the continuation payoff of an insider. And there is this n minus k minus 1 others that if one of them join, you get the continuation payoff of being an outsider with a larger coalition. So then we can know, of course, that once you reach theta, that you sign an agreement. So if adding one agent to a coalition gets you to theta, then this continuation payoff is simply pi s theta if you're part of the coalition, and pi n theta if you're not part of the coalition. And with knowing this, and then knowing also that outsiders need to be indifferent, we can get a solution for the hazard rate. So what does it mean for outsiders to be indifferent? They need to be indifferent between the continuation payoff of being an outsider at K and the continuation payoff of being an insider at K+1. Or if you want to say it differently, they need to be indifferent between not playing a hazard rate and being at K, or joining immediately and becoming part of this group. And the interesting thing is that if you fill that in, if you use all this information and you fill that in these functions that we had before, then what you get is that actually the hazard rate does not depend on our K. It only depends on theta. So I thought it was mathematically like a nice result. So it means that like, it doesn't matter where we start or how far we are from the goal we're trying to reach, only matters which theta we're trying to get to. At every stage towards getting there, each outsider will have the same hazard rate with which they mix. That also means that if you're far away from your goal, the total sum of these hazard rates is going to be larger. So you'll approach your goal faster if you're still far away, and you approach your goal slower once you get closer. And then what is the hazard rate? It's this function. It's a combination of this R plus sigma, the payoff as an insider, the payoff if you don't sign anything, and the payoff of an outsider. And it's also a function of the difference between the amount of agents you have and what you're trying to reach. And one thing that's interesting to keep in mind is that it's linear in this R plus sigma. So with that, we have the third condition satisfied, because we now also like, I think it's easy to see that this is always going to be positive. So there is indeed always a positive hazard rate with which they mix. So that means that we have condition C satisfied, and now we just need that the coalition members need to be willing to wait until theta, and that turns out to be the hardest one. Okay, so what does it mean for them to be willing to wait? It means that if we start at some alpha, then at every K along the way until you reach theta, their continuation payoff at K for waiting needs to be larger than the payoff for signing an agreement right now with this current coalition size. And if we only look at theta minus 1, so suppose we set alpha equal to theta minus 1, which is mathematically the easiest one to like solve, because it only gets more complex looking if you go further away. And we fill in the H that we found before and mix it all around and solve it, then you're just gonna have to trust me that you get this. So this is the condition for the coalition to be willing to wait for one more agent to join if we start at alpha being theta minus 1 for any theta. Now you might see that this does not depend on sigma and R anymore. So already filling in the hazard rate in just these continuation payoffs, just here without doing this inequality, already removes sigma from the equation. But then once we set this greater or equal to this pi sk, we also lose R. So to some extent, the hazard rate will compensate for the value of sigma and R that you fill into the model, and will balance it out to a point where whether or not something is in equilibrium is only going to depend on the actual payoff functions that you get, and no longer on like the delay or the chance of failure. On the other hand, this is what we get, and there's not much more that I can say about it, except for that if it satisfies this, then we can have an equilibrium, and if it doesn't satisfy that, then we don't. So that's unfortunately sort of the negative news here. It's not a very sharp result. But then once we had this, we wanted to like know a little bit more about like how does this depend on certain parameters. Oh, one more thing before I go there. So we did then look into specific emission games. If you fill in these underlying like cost and benefit functions, specific type of emission games, like what do you find for these specific scenarios? And that's when we find that actually for a lot of these applications, or the ones that we've tried at least, you find that the largest equilibrium coalition size that you can get is this KST, which is then also the only one. Sometimes you get also a slightly larger one, like one larger, maybe two, but that's only if your N is relatively small. So this is kind of this paradox of these climate agreements again, what I mentioned in the earlier part, which is that if you have a large set of agents and potentially a large benefit of everyone collaborating, that's exactly when you're not going to be able to get a large coalition. So we're kind of back there. But then since these other papers had very positive results from repeated periods, we thought, well, maybe that's also going to help us. And so the first step to going there is we wanted to look at what if this pi zero, so the flow payoff you get while you're waiting or when you get a failure, if that increases, does that make anything better? And so we did the comparative statics for that, and it turns out that, you know, as long as you assume that the coalition is indeed still going to wait for one more agent to join, so your continuation payoff is one that assumes that they're still waiting, then a larger pi zero is going to increase the value of your continuation payoff, which means that if you make pi zero larger, you can have weakly larger coalition sizes in equilibrium. And I will show you in a bit why this is relevant for the repeated setting. Don't want time? Oh, plenty of time. So I will show you how this works, but just to like spill the beans already a little bit, what we get from this result is that once you allow for multiple negotiation rounds, you will indeed weakly improve the equilibrium coalition sizes that you can get out of the model. This is the part that we're still kind of like working on, trying to see if we can get some more results out of this. So there's just some preliminary results here. So let me show you first, what does the model look like if we allow for repeated negotiation rounds? So what we get in this case is that now if the negotiations fail, it's not that you get pi zero for forever. You have some kind of delay, 1 year, 5 years, whatever is reasonable. Some delta t that you have to wait. And then otherwise, I mean, alpha and theta are still alpha and theta. We're going to assume here that if we start a new negotiation round, we start with the same alpha and the same theta, but it might be a different set of countries. So that means that if you were assigned to be a coalition member the first time around, you might not be the next time around. And we're assuming that this, yeah.
Is this necessary or helpful anyway? Because that's exactly the opposite of what you said before, for this set of countries assigned to deploying you, right? You're saying that like
That is news, yeah. So it matters for the analysis, and I have not looked into what happens if we assume that it's the same set of countries. The only thing I can say about that is you would expect more optimistic results under this assumption, because you're in this case, of course, it hurts a bit to have failure because you have to wait, but it also benefits you because now you might be an outsider instead of an insider. So yes, it does matter. I don't know how much it matters because I haven't like looked into the other option yet.
make it much easier. Sorry.
This version? I don't know if it necessarily makes it, I mean, I guess it makes it easier to argue that you get more optimistic results. I don't know if it necessarily makes it easier to solve the whole system of equations. Yeah. Okay, so lastly, we assume that if we start a new negotiation round, that the strategies do not change. I mean, again, you might not be an assigned country anymore, but you might be an outsider, but you play according to what the outsiders are expected to play then in that case. So then when you look at the continuation payoff, you can sort of predict what will happen in the next round, and that makes the analysis doable. this is a lot of math again. I'll do it one step at a time. So I'm gonna use delta for this e to the power of minus RDT. So this is just your, if you have to wait for the next negotiation round, then this is your delay. So now our failure payoff by 0, so that's like the payoff that you got when sigma happens, is now this other item, which is like, while you're waiting for the next period to start, you still get pi 0, and then once the next period starts, you have alpha over n probability that you're going to be an insider, and you have n minus alpha over n probability that you're going to be an outsider. Okay, so now if we rewrite this continuation payoff for insiders, it looks like this. So this part is still the same. Of course, while you're waiting for something to happen, you still get pi 0. But now if there's a failure, you get this value v here. And we can rewrite this whole thing like this. So basically what I'm doing is I define this new pi 0 prime, which is r times pi 0 plus sigma v divided by r plus sigma, so that in this thing, I can make it look like the way it looked before, but where I used to have my pi 0, I now have my pi 0 prime. And so what I want you to see is that pi 0 prime is a weighted average between pi 0 and its v, and v is clearly larger than pi 0, because it contains pi 0, 1 minus delta, but at delta, it contains this combination, and the continuation payoffs always have to be at least pi 0, because you can't get anything less than pi 0. So pi 0 prime is in fact larger than pi 0, and we just learned that increasing pi 0 has a positive effect on your continuation payoff, which has a positive effect on being able to reach larger coalitions. Now, another thing is that we can also see that if you're more patient, for example, changing R, or if the delay between negotiation rounds is shorter, then delta is going to be closer to 1. So this term is going to be less pi 0 and more continuation payoff, which will also increase v, also increase pi 0 prime. And so actually making the delay between two periods shorter or making the agents more patient also has a positive effect on your probability of getting a larger coalition size in equilibrium. So that's as far as we've gotten right now. This, by the way, right now, I can only say this for if we start at alpha at theta minus 1. And that is because at that value, my H is the same effectively as it is in the 1 period game, where again, you have to replace pi 0 by pi 0 prime. I am relatively convinced that just as in the 1 period game, H does not depend on K in this one either, but I haven't shown that yet. So right now, I cannot claim that this whole analysis is also true for smaller K. But I think it holds. So I'm just going to leave you with that. Okay, so I think I'm finishing a little bit faster than I had to.
I just happen to have a question. So
Yeah.
Might as well. I was wondering, at the beginning you said, despite the paradox, larger coalitions do form. And I was wondering also along the lines that you mentioned that there were definitely some countries who were absolutely definitely joining even in multiple rounds. How the investment change as they join? So some of the papers cover the investment as well, because surely the terms are changing as well as some countries join.
Yeah.
And I guess this is captured by pi 0 getting
So,
larger and larger.
You mean so there's two things. There's one, like how much you're going to reduce your emission.
Yeah.
And there's another, what's usually referred to as investment in the literature, which is how much you invest in like green technology and things like that.
Yes.
So how much you reduce your emission depends also, like how that depends on the size of the coalition. Depends also on the underlying emission game. Like some model it linearly, some model it quadratically. So that's going to make a difference.
Okay.
with investment in green technology, what this earlier paper that I mentioned shows is that the problem is if you have more green technology, it's cheaper for you to reduce your emission, so you introduce inequality in that sense, or asymmetry, I should say. And that puts you in a worse position because you already put money into green technology, but now you get to be the one that also has to reduce their emission more because for you, it's relatively cheap to do that. Whereas for your neighbor, it's still like as expensive as it was before. So that's why if you don't reach a sizable agreement right now, there is an incentive to not actually invest as much in green technology because you don't want to be the sucker that next period has to reduce their emission more just because it became cheaper for you because you did your homework in the past.
And might be also literally in the case of Australia behind this, as when they introduced the quotas, they got negative.
Negative quotas.
Yes, they got negative quotas.
Okay, I wasn't aware of that.
They could increase their emissions.
So that's interesting.
That was part of it.
Yeah, well, see, so that's the problem.
You should talk to other people because they really upset about this.
Yeah, I can imagine because that kind of.
Yeah.
That doesn't look good. Yeah,
Two questions about your mixed strategies. So, is it by assumption that the hazard rate is fixed and not dependent on time, or is it the result? Probably by assumption, right? Because
yeah, so what I said, like in this paper, we only look at that type of strategies that don't really depend on time. Just to limit our search for like what kind of situations you might get.
yeah, and I mean, this kind of like makes your interpretation for these hazard, I mean, or this interpretation of mixed strategies really weird in a way, right? Because it doesn't matter, I mean, how much time is going on. I only have always like every minute I have a fixed chance of, yeah, maybe I'll sign now.
Yeah.
Or lately, maybe I'll sign. It doesn't, nothing changes, right? You don't have any end time effect because you don't have an end time. You don't have any other
Yeah.
effects, and
No, so
the
effectively in the model,
results
it
would
says-
be different if you use whatever behavioral strategy, yeah, the other one, right? Where you just choose a path, you randomize between a path, right?
I thought
Random-
behavioral study was exactly the ones where you don't know where you are exactly indicating. Maybe I'm mixing those up.
Doesn't matter, where you
Okay.
randomize it over paths, right? Where you say, oh, I'm never gonna commit, right? Or I will commit, but at this time, or at
Yeah.
this random time, right?
So,
If you randomize them over these, then actually the result will be different, right?
so what we can model is if you have a country that says, I'm never gonna randomize. That's easy to incorporate in this model. It's effectively the same as saying, I just have one fewer country in my game. You could of course look at one where like different points in time, they use different hazard rates, but then the combination of those hazard rates will still have to be in equilibrium at every point in time.
Yeah. I mean, it's
Um,
complicated and everything basically.
But yeah, that might differ because of your future hazard rates. My suspicion is that it all gets very complicated. And so like, I agree with you, it's interesting. I'm not sure how, I mean, it might be the kind of thing that you can solve with like simulations or like if you run it with a computer. I'm not entirely sure. Algebraically, I would be able to get anything out of that. What I find an interesting thing to look at is how if you incorporate beliefs into the system and say, well, you might change your beliefs on how likely someone is to join based on how long they haven't joined yet, for example. Because now we're all saying like, okay, well, I know that everyone is randomizing, so I know exactly that the probability you're gonna join in the next second is, well, whatever computed based on the hazard rate is that probability. But of course, in real life, there is a strategy with like playing hard to get kind of, where like if you pretend that you're not gonna join ever, then people might lose their faith in you actually joining, and they might be like, okay, we'll go ahead and sign without you. So that's an interesting alternative that I think is worth considering, but I haven't had the time to do that, so I don't.
I mean, you could also model I mean, it wouldn't be technically mixed strategies anymore, but they are beforehand mixing between, I mean, joining at a certain time, right? I
Mhm.
mean, for this only works if the R is 0 in this thing, because otherwise there's no reason to join later.
Yeah, or if you make it incomplete information. So I would say if you're randomizing over like whether or not you're gonna join or at what time, it would be interesting to add incomplete information where you don't know what other people's strategy are. Because then indeed you can say like, well, there is a point in waiting because maybe someone else joins before me, right? Because you don't know. But yeah, that's an interesting idea.
I'm thinking about theoretical agreement in which, and I don't know if whether it can be included in this framework or not. I suppose the later, but I'm thinking about an agreement in which you have a kind of negative externalities increasing in time. I consider, for example, if you have an agreement and the countries who come to an agreement agree that, for example, they will decrease the trade with the outsiders in each year by 10%. And then what?
A kind of punishment.
Yeah, punishment, yeah, kind of punishment, but they punish themselves maybe also because trade is at some kind of level beneficial for them as well. But so I don't know, what's your opinion about it? I think it cannot be included in this model, but maybe some extension, I don't know.
I mean, I would think that should be a way to put pressure on countries to become part of the agreement, yeah, that should work. And the idea of punishments that also hurt you is not new to the literature, like I don't know it necessarily in this context, it may have been done, but I'm just not entirely sure. But I definitely know some other like infinitely repeated games kind of settings where they have this kind of like trigger strategy which hurts you as well, but it's just to deter the other person from doing the non-desired behavior. So yeah, I think that could be something there where you can just push up the size of the coalition simply by saying, we'll make life really hard on you if you don't. Yeah.
Sorry, I was thinking about a different kind of situation where your model is actually, and I was thinking the US Congress, the federal budget negotiations, and when the different factions have to come together and extend the budget, unless they get this federal shutdown. It's a little bit similar. But I think that the main difference is that they have issues, right? And they want to agree on some issues. So okay, put restrictions on immigration or send money or don't send money to Ukraine. But in this sense, it's similar here because you have to agree on different areas. Just fine.
I mean, it seems to be one difference, because if I remember correctly, in the States, one of the issues was that they gave everyone like veto right at some point. Like, I think that was what recently was the issue, was that, I don't know if everyone had veto right, but like, they agreed to like certain people at least, or like subgroups of people having veto right, and that gave them then of course a lot of power to say, I'm not gonna agree with anything unless you do exactly this one thing that I want you to do. That's my understanding of part of what went wrong there. Which luckily I think here we don't have that, because at least if someone is playing like difficult, the rest can still do something that's still useful and beneficial. It's just maybe not as good as when the other person has joined as well.
Yeah, but my problem is that in these summits, usually people at the end write some agreement, right?
Yeah, I think one thing.
Write some agreement. They just don't include or include.
Yeah, I think one big thing that we're missing in most of this literature, as far as I can tell, is that, and one thing that we're also not covering is, we're just saying, oh, you're gonna maximize cooperatively your benefits, right? But like in reality, it's so much more complex. It's all about like, oh, you have to do this much and you have to do that much, and this country is gonna argue that it's very costly for them to like produce by this much or that much. So there's, even within the negotiations, there's still so much extra going on. And so many details that we're just completely abstracting away from here. So yeah, I think, I mean, I can see how like, yeah, if you look at those details, you might get like a similar situation going on as what the States have, and I don't know right now how to model that in theory, but I think there's definitely something that is missing here.
I'm
interested in the last result you presented, because it's sometimes counterintuitive to me. It's one about, so if countries get more patient or the time periods get smaller, when they reach larger
The
agreements.
delay between periods gets shorter.
Yeah, so I see that makes sense mathematically, but my intuition would be that the kind of rate of constant waiting, the more pressure there is to reach a large agreement now. It actually, it's not that you find the opposite.
No, so what happens in these models is like, that's why the static model is very pessimistic, is because the outsiders can say, I'm gonna stay out, and they know that the coalition is gonna sign anyway. Because in the static model, it's very extreme, right? Like, I mean, whatever size you get, you might as well sign, because any agreement is better than no agreement. So basically, anyone can stay out that benefits from staying out, because you still get the benefits of these other people having an agreement. And you have like a sort of moderated version here, which is that if it's not so painful for us as a coalition, if we have a failure and we have to wait, I don't know, only like 1 month or something like that to start again, then that allows the coalition to put way more pressure on the outsiders, because they can like truthfully or like convincingly say, well, we are not going to sign unless you join us, because it's actually worth it for them.
Yeah, sorry, that's, can you model in the majority of the pressure coming from, all right, if we're not agreeing now, maybe you're not the outsider next time.
Yeah, so that's one big part here is indeed that like it's even beneficial for you if it fails, because you might be the outsider next period. So that's indeed like what you referred to earlier. It's like interesting to see like how that changes if you know that you're going to remain an insider, because you're definitely going to have a smaller effect of the repeated negotiations, because it's a smaller, you don't actually benefit from the failure, you're just not hurt by it as much as you were without the repeated negotiations. Okay, then very quick summary. Just in case you forgot in the last 5 seconds. Okay, so we build a model of climate coalition formations where we actually try to model the process of forming this coalition. We use continuous time to do that. And in that model, we look at 2 types of strategies. We look at a pure strategy, where we find that you can have any coalition size as an equilibrium size, as long as it's at least as large as the equilibrium size in the static case. Then we look at mixed strategy equilibria, which allow for possible failure on the equilibrium path, as well as for delay on the equilibrium path, which is what we kind of also wanted to be able to have in our model, but the results on like the equilibrium sizes are not that sharp. And then we look at multiple negotiation rounds, where we find that larger coalitions may be possible because of the negative effect of a failure not being as bad. And we find that this effect is stronger if delta is smaller. That's it. Thank you all for your attention.
I guess you already answered the Q&A, so thanks for